Okay, so now we're going to begin our probability unit. We're going to start with some basics of probability and how we express probability when we do that in statistics. When we think about chance and probability, we tend to think in terms of percent. That's in everyday language. But in stats, we're always going to convert these percents to decimal forms. And that always means just simply moving the decimal place 2 places over to the left. So we don't say 9%, we say 0.9, 0.2, 0.826. Now, as a personal thing, I like to put a 0 in front of each decimal place, for each decimal point, just to make it a little easier to see. I just think it increases the readability. So I encourage you to do that as well, but not really a big deal. But you'll see that as we move through, just so you know why that's there. A basic probability, flipping a coin, rolling a die, that in and of itself is not terribly complicated. What makes it interesting, what makes it complex, is when we start introducing multiple probabilities and when we start thinking in terms of ands or ors, of multiple different outcomes. So as part of our introduction, let's go over some of the basics, math behind these probabilities. Here is a 20-sided die, ranging from 1 to 20. So what are the chances of rolling a, say, 19 on a 20-sided die? What are the chances of rolling a 3 or an 8? Well, simple enough. There's 20 sides. They're all equally sized, equal chance of coming up. So any particular number is 1 out of 20. Okay, fine. What are the chances of rolling a 1, 2, or 3 on a 20-sided die? Do you think that probability should be higher than just rolling a 1? Or do you think it should be lower than just rolling a 1? So what should it be? Should it be higher or lower than just 1 out of 20? Well, if you have multiple ways to get this requirement, this idea that like you fulfill the requirement of getting 3 or less, there's 3 different ways to do that, then that should mean it's more likely. It's more likely to get a 1 or a 2 or a 3 than it is to get a 2 or get a 3 or get a 1. Okay? Because any one of those 3 options takes us to where we need to be, 3 or less. So, in all reasonableness, this result should be greater than 1 out of 20. How do we figure that out? How much greater should it be? Well, in this case, you have to think in terms of the numbers we're working with, right? We're not really working with a 1 out of 20 will become a 5% chance. We're not really working with 5%. We're working with 0.05. Right? Each one of these is a 5% chance of 0.05. So the result, whatever we do, whatever operator we put in here, should result in a higher result. If it's multiplication, you multiply a bunch of stuff that's less than 1, you'll get something even smaller. But addition, means it comes up, right? It increases. Right? There's a 15% chance, or 3 out of 20, right? 1/20th plus 1/20th plus 1/20th, to get a 3 or less. We can do this addition because each result is mutually exclusive. Each result is mutually exclusive. If a 1 is rolled, that means at the same time a 3 cannot be rolled. Right? Choosing 1 or having 1 result excludes all other results. Multiple results cannot happen at the same time. Because each possible outcome is mutually exclusive with all other possible outcomes, then that means the sum of all probabilities must equal 1. Not 100, 1. Probabilities of all possible outcomes must equal 1. In this case, this is obviously true with the 20-sided die. You take 1 over 20, you add it together 20 different times, or you just take 1 over 20 and multiply it by 20, you're going to get 1. So if it's mutually exclusive, the word or means we add probabilities. The chance of fulfilling the criteria should increase. It should get higher. And yeah, here's another 20-sided die. If I roll this die and this die at the same time, what are the chances of getting a 1 or 2 or 3? Well, now it's gotten a lot more complicated, because now rolling a 1 here does not prevent having a 2 be rolled over here. Right? While 1 is still mutually exclusive to the other ones on the yellow die, it has no bearing or impact or influence on the result of the black die. So if we were to figure out the result, a 1 or 2 or 3, on these two different dice, that becomes a lot more complicated. We have to think about all the different possibilities of these two results. Like this could be a 1 and a 1, this could be a 1 and a 2, this could be a 1 and a 3, this could be a 1 and a 4, 1 and a 5, 1 and a 6, etc., etc., etc. All the way down to 2 and 3 and 4, There are how many different possibilities? 20 over here, 20 over here, 400. So in that way, you would have to really figure out the likelihood of getting a 1, 2, or 3 on at least one of the dice. You would have to think about all the different possibilities and then figure out how of those 400 possibilities, how many have at least 1, 1, at least 1, 2, or at least 1, 3. And then when you've listed all those mutually exclusive possibilities, all those mutually exclusive pairs, because now when it's pairs, all mutually exclusive, then you can count up, okay, maybe there's like 10 or 20 or whatever it is, divide that by 400, get a probability. I could do that now, but I stupidly picked 20-sided dice. I am, however, much more willing to do it on 4-sided dice. So these are 4-sided dice. The result is whatever number is at the top. That result is 4. That result is 2. That result is 1. And I got 2 of them. So there are, of course, 16 possibilities. Let's list all the possibilities of red and yellow. So what are the chances of getting it? So here's all the possibilities I should say, right? You can see the way I organized it is I just picked red and I just figured out, okay, if it's red, I have a 1. That means let's list all the possibilities for yellow, etc., etc. Now, my 1, 2, or 3 option, this is actually really easy because the only way that you get neither 1, 2, or 3 on either die is if you both get 4s, and there's only, of course, one combination for 4. So now it's even easier. We don't need this. We can just say, well, all of the sum of the probabilities must equal 1. What are the chances of getting a 1, 2, or 3? Well, the only way to not get that is to get 2 4s. So naturally getting a 1, 2, or 3 is the result of is a 15/16th chance, right? That result is the same thing as what's 1 minus the result of getting only 4s. If I did 1 or 2, well, that's a little bit more interesting. So in this column, we have at least 1, 1, or at least 1, 2. And then those as well. So now we have 8, 9, 10, 11, 12. 12 divided by 16. So what are the chances of getting a 1 or a 2? Which is half the results, right? It would be a 50% chance on this die. But what's the chance of getting at least 1, 1 or at least 1, 2? It's more than 50% chance. It is 12 over 16, 75% chance. What are the chances of rolling 2 4s on two 4-sided dice? Well, like we said, that's a 1 out of 16 chance. But is there a way we can mathematically derive that without having to make that whole chart of all the possibilities? Sure. Keep in mind what we're asking. We're asking what is the chance of one of them becoming a 4 and the chance of another one also a 4. Note 4 and 4 is not mutually exclusive. You can have, just because you have 4 in one doesn't mean you have 4 in the other. So let's express this. This is of course 0.25 or 1 out of 4. This is 0.25, 1 out of 4. Again, expressing things as a decimal. Now, the chance of getting 1 4 is obviously 1 out of 4. Should the chance of getting 2 4s be higher or lower? Well, rather now of saying or, we're saying and. It's one thing to say either of these have to happen. It's quite a different thing to say both of them have to happen. And if both of them have to happen, if you're adding requirements for something to happen, then it shouldn't become more likely. It should become less likely. And the way that you make things less likely is by multiplication. Again, remember, these are all less than 1 by definition, or equal to 1. That's a pretty boring probability. And so because they're all less than 1, if you start multiplying them together, it gets smaller and smaller. Because of course, 0.25 is the same thing as 1/4. And 1/4 times 1/4 is 1/16. We can do this because each of these probabilities are independent from one another. So the results always go down. And if I were to add a third 4-sided die, 4 and 4 and 4, then it will be 1/4 times 1/4 times 1/4, or 1 out of 64. So generally speaking, if we are going to multiply probabilities independent, if we are going to add probabilities, they have to be mutually exclusive. To give counterexamples to both of these, consider mutually exclusive, and we're pulling cards from a playing card, or from a deck. So there are 4 queens in the deck of cards out of 52. There are 13 hearts out of the deck of 52, which of course we can simplify to 1 out of 4 and 1 out of 13, or 1 out of 13 for the queen, and 1 out of 4 for the heart. So what is the probability of drawing a queen or a heart from the deck of cards? It's like, well, we can't just take 4 out of 52 plus 13 out of 52 and say, well, that's the probability. It's 17 out of 52. We can't do that because this one is not mutually exclusive to this one. Right? Just because you are pulling a queen does not mean you cannot also pull a heart. Unlike a d20, when you roll a 1, that means you cannot roll a 2. But you can pull a queen that is also a heart. You have to include the one that's both. So these are not mutually exclusive. Similarly, imagine you are pulling cards from a deck and you pull 2 cards from the deck. What are the chances both cards are aces? Well, that sounds straightforward enough, but keep in mind, when you pull a card from a deck and you keep it, you are now changing the probability based on what you pulled. In the first trial, the chance of getting an ace is 4 out of 52. If you pull an ace in that first pull, the chance of getting another ace is 3 out of 51. Right? There's 1 fewer card and there's 1 fewer ace. If you do not pull an ace, the chance is now 4 out of 51. Right? If you imagine, let's imagine we pull like 5 cards from the deck. What are the chances that you get 2 aces? That's actually a really complicated problem because the chance of subsequent pulls is going to change based on what you got the first time. So again, it's helpful to think of then, in order to do this, you have to think of all the possibilities. That's the easiest way to do it, honestly. Think of all the possibilities. And we can help map out all these probabilities and all these possibilities with a tree diagram. Now, we're not going to do deck of cards. That's a bit too much. But we're going to do a simple example. So let's imagine you're getting 2 packages delivered. Package A has an 80% chance of arriving on time. Package B has a 90% chance of arriving on time. What's the chance that at least one package will arrive on time? One way to answer that question is to figure out the chance that neither of these arrive on time. So that would be 0.2 here and 0.1 here. Multiply them together. That's the probability that neither arrives on time. And then subtract that from 1, and then you get the probability of at least 1. Okay, that's simple. But what's the probability of exactly only one arriving on time? In other words, both don't arrive on time, but also at least one does. One does, and only one does. Let's map up all the possibilities. So, for one, let's recognize that these are independent. So just because A arrives on time does not mean B is going to be late or arrives on time. Doesn't change this probability. This is always 90%. This is always 80%. So let's start with A first. So in this case, there are 2 possibilities. It's on time or it's not on time. So I draw 2 lines emanating from A. Each of these lines has a probability associated with it. On time is 0.8. Late is 0.2. Again, it's either one of these 2 things. So one event has an 80% chance, and the other event must have a 20% chance. If one event is 0.8, then the other event must be 0.2. From this path, we can then create a new path. There are, if it arrives on time, there are 2 different scenarios. If it is late, there are 2 different scenarios. Because B is independent from A, then this will be exactly the same as this. Kind of extending things outward a bit just to make it a little easier to see. That line is just going to be a reference. And this is on time, late, just to save myself some room. These things get really big, but they're very helpful because it's very easy to miss a possibility unless you map it out. So I encourage you to map it out, especially when you're getting the hang of this. And now, each one of these scenarios is mutually exclusive to the other. If this happens, A is late and B is late, then this cannot happen where A is late and B is on time, because A can't be on time and late at the same time. Even though A is late in both of these scenarios, each one of these paths represents a unique sequence of events, a unique sequence of outcomes. So we can figure out the possibility of each event, or each outcome, by multiplication. This happens and this happens. 0.72 for probability. So note a couple of things. 1, each one of these possibilities, each one of these outcomes is less than the values that preceded it. This 0.72, while high, is less than 0.9, is less than 0.8. It has to be, because you multiply these 2 values that are less than 1 by each other, you're going to get a smaller result. So naturally, it is less likely that this will happen, A and B arrive on time, than it is for just B to arrive on time, than it is for just A to arrive on time. 2, it doesn't matter that I said A and then B, because they're independent, right? If I had swapped them, it would change the order of where things are, but it wouldn't change the logic. 3, note that if we take these 2 values, right, this or this, they add up to 0.8, which equals this. And if we take this or this, right, 0.18 or 0.02, they add up to 0.2. They have to, because this is 0.2, and then it's split between these two options, and those add up to 1. So then mathematically, these two results have to add up to that original line. And when we take all of these options together, we get 1. That's one way to check to make sure you didn't miss anything, is to add up the probability of all outcomes. And if all of them equal 1, then you got all your possibilities, no likelihood. If they ended up with more than 1, then you did something wrong with the math or with the setup, counted something twice. Now we can ask ourselves, what is the chance of getting exactly 1 on time? Well, there are 2 ways to get exactly 1 on time. A comes on time, but B does not. And A does not come on time, but B does. Scenario 2, I guess we're going to call it scenario 2 if you want, plus scenario 3, or this, right? Also known as this happening or this happening, gives us 0.26. So even though 90% chance of one of them showing up on time, 80% chance of the other showing up on time, it seems really likely that both will show up on time. There's actually a 26% chance that only one will show up on time. This is only a 28%. It's a 28% chance that both of them will not be on time, which makes sense, of course, because 0.28 plus 0.72 is 1. Now, when I'm doing these tree diagrams, I'm assuming they're independent, which means this part of the tree is the same as this part of the tree. As we will discuss later, when we do Bayes' theorem, that doesn't have to be the case, right? We can actually map out what's called conditional probabilities. Well, this part might change, like if B is late, maybe because there's that might cause. If A is late, that might cause B to be late, and so forth. That can get a little more complicated, but for right now, this is a good way of thinking about all the possibilities. Okay, let's go a little bit more extreme. Let's imagine that you work for a construction company and you're working on this new project, and at every stage, it's hard to tell exactly how long it'll take. But from experience with this kind of project, you know certain things. You know that demolition on the first stage of the project, it could take 1 month or it could take 2 months. There's a 40% chance of 1 month, or 0.4, 0.6, or 60% chance of 2 months. For foundation, it can take 4, 5, or 6 with a probability or P of 0.1, 0.4, 0.5. And for the actual building of the building, it can take 6 or 7 months, or 0.2 and 0.8. 80% chance it'll take 7 months, 20% chance it'll take 6 months. Now, these are all independent from one another. So if it takes a long time on the demolition, that doesn't mean it's going to take long on the foundation or quick on the foundation. They're all independent. And in practice, of course, construction is much more complicated than that. I'm not saying that this is all mapped out so cleanly, but I like this example because it shows all the different possibilities, and you can see there's lots of different possibilities. There's actually 2 times 3 times 2, or 12 possibilities, but it's kind of hard to think about them all, and you can really illustrate the value of the tree diagram. Here is the full tree diagram of this scenario, taken from my notes. So you see we start off with 1 month or 2 months for the demolition, and then 4, 5, or 6 for the foundation, and then 6 or 7 for the actual building. And you see, of course, the top half is identical to the bottom half because these are independent. And each one of those building nodes, each one of those building branches is indistinct from the other one. They're all exactly the same. But of course, you take all these different options and you can get this thing done in either 11 months, right, as fast as it can be done, or up to 15 months, which is the slowest it can be done. But obviously, some time frames are more common than others. It would be nice if we could do a similar probability, right? Do 0.4 times 0.1 times 0.2, 0.4 times 0.1 times 0.8, 0.4 times 0.4 times 0.2, 0.4 times 0.4. Hey, that's hard to do. Let's do this in Excel. That'll be easier. So we can do this relatively easy in Excel. There's no built-in diagram for this, but it can be just a simple matter of copying and pasting. For example, this is why it's nice to have the tree diagram already out. We know that from this 0.4 option, we have 1, 2, 3, 4, 5, 6. And from this 0.6 option, we also have 1, 2, 3, 4, 5, 6. So let's do, oops. I mean, it is a percentage, but let's just make this nice and clean. 6 options of that and 6 options of that. So in other words, this is one of the branches. This is 1/2 of the branch, and the other one is the other half of the branch. Then from 0.1, we have 2 options. 0.4, we have 2 options. 0.5, we have 2 options. So let's just do that. 0.1, 0.1, 0.4, 0.4, 0.5, 0.5. And again, we're going to get rid of that thing. I don't know what happened there. And then we can just copy and paste it because it's identical. It's exactly the same. Then from that, say 0.1, we have 2 options, 0.2 or 0.8. 0.4, we have 2 options, 0.2 or 0.8. 0.5, we have 2 options, 0.2, oh look, it's the same. Because of course it is independent. So we can of course copy, so we can, you could if you wanted like do this, but then this will project outward if you do that. You don't want to do that, so you can copy and then just highlight the whole thing, and then it'll just recognize you're trying to do 0.2, 0.8, 0.2, 0.8. And now note that we have unique scenarios across the board, just like sort of what I did with those dice, when I had a whole bunch of 1s and then 1, 2, 3, 4, and then a whole bunch of 2s and then 1, 2, 3, 4, and so forth and so forth. These are all the possibilities. And then we can just, you can do, you know, A1 times B1 times C1 and get the result there. Again, I'm going to get rid of this thing. Or if you want, you can also just be really fancy and just use the product function, highlight across the board, do the same thing, copy and paste it down, and look at that. These are all the possibilities. If you want to switch to percent, maybe throw in a decimal to make it a little easier, you can see it. These are all the possibilities. And then we can just 11, 12, what did I say before? 12, 13, 13, 14. So that is our mutually exclusive story, or our, so that is our independent story. Multiply each of those values across the board and you get this scenario. But now maybe someone is wondering, what are the chances of it coming out to 13? Like, what is the chance that this will be done in 13 months? What are the chances it'll be done in 12 months? Well, there are multiple ways to get to 13 months. You could go this route, this route, this route, or this route. In other words, this could happen, or this could happen, or this could happen, or this could happen. You add. Let's make this a little easier on ourselves. Select all, go into data, go into sort, and we're just going to sort by column E. And now all the different scenarios that have the same number of months are next to each other. So for 11 months, it's just going to be, it's going to be this one. That's boring. For 12 months, it will be 0.32, 0.32, or 3.2. So for 12 months, it'll be 3.2%, or 3.2%, or 1.2%. So we use our sum product add them all up, or is a 7.6% of 12 months. We can sum up all 4 different scenarios for 13 months. Sum up all 3 scenarios. So note that there are 3 scenarios for 14 and 3 scenarios for 12. However, 14 is a lot more likely than 12. And there's only 1 scenario for 15, but 15 is still pretty likely. And so now we have a nice rundown, right? What is the chance of it being like a 15-month project? What is the chance of it being a 14-month project? And this is helpful not just for the client's perspective, this is also helpful for your scheduling perspective as someone who might be working for a construction company trying to figure out, well, what kind of jobs can we handle so we don't get backed up and people get upset at us. How can we make sure, but you don't want to go the other way because you don't want your people to be idle either. You don't want to have no jobs going on. You always want to have a job. You always want them to be working because you're always paying them. This is the basics of working with probability. Hopefully you get a good sense of this or versus and. Again, or is used for mutually exclusive options. This happens, or this happens, or this happens. You can add them up then. And is only used for if they're independent. This and this and this, in which case you can multiply them. Now, as mentioned, if you do conditional, if you figure out the conditional probabilities and sort them out, you can also use and that way. And that's something we'll be talking about as we move forward with this. And we'll do more of these as we get into expected value, which is the next video.